All right, good afternoon, everybody. So what I would like everybody to do is download everything for today's lecture. I have the directions set up, and please just download that. What we're going to do today is we're going to finish up our discussion of binomial heaps, and then we're going to introduce one last advanced data structure, and it's going to be called a cuckoo hash. And the objective of the cuckoo hash is to be able to improve upon the double hash and quadratic probing that we have been using so far this semester. And one of the benefits of a cuckoo hash is that, well, there's two main benefits that you're going to learn about today. The first one is that by setting everything up, we're going to be able to have a significantly more full hash table before rehashing. The math says that we can get up to 91% without rehash, as opposed to a conventional hash linear probe hash table where you need a hash when it fills at 50%. So we're going to work on those problems, and then we will we'll get on this. So first, one last thing. You're in the process of scheduling your pre-internship demos. I posted this link on the Slack, but I'm going to have it here as well. What I would like you to do, once you know the date, time, and the link that you're going to use for your pre-internship demo, please put it on this Google Drive. I'm trying to stay on top of it as best as possible, but there's 40 pre-internships this semester, so some of them might slip by me. So if you're able to do that, I can make sure that I can be in attendance for all of them. So I want to make sure that I'm able to be there when you present your final work. So if you could do that for me, I'd be really appreciative. All right, so what I would like you to do is, once you have this downloaded and you're in your lecture 25, what I'd like you to do is I want you to run the command make prob3. And in make prob3, what we're going to do is we're going to perform some insertions, and then we're going to remove the minimum from the binomial heap. So problem 3, we're going to work through it together. And then you're going to do problem 4 together before I go over to the whiteboard and we work on a solution. And then we're going to introduce cuckoo hashing and work on a problem with that as well. So as with red-black trees and splay trees and B trees and AVL trees, there is a good working example of a animation online. So you notice here that it'll say binomial Q. If you look at the official NIST, the National Information of Science and Technology, they will describe that sometimes it's called a binomial queue because binomial heaps are often used in priority queues, but that the official term is binomial heap. So we are going to stick with the NIST standard. But in case you're wondering why it says binomial queue, that's why it says that. So the first thing we are going to do is we have the characters AH, B, G. So I'll read them over to you here. We're going to do AH, B, and G, C, F, D, and E. And just like everything else, if you go to the lecture notes and schedule, will provide you a link that will take you straight to these particular problems. So there's the final exam review guide under lecture 27. And if you go here, that link that's there, that's taking its sweet time downloading. In the link that's here, this will take you straight to lecture 25. And it'll have the images just in the same way that I would present an exam. So here we have lecture 25. I could click on this link and it will come here. We skip past these and it takes us straight here to this problem. So remove smallest, extract min. That's the type of thing that will be on the exam. So what I want to do is walk you through and ask for you to tell me what you think the first 4, how the binomial queue is going to look after our first 4 insertions. So I'll do the easiest one. A is just A, right? And so the next one is the letter H. So somebody tell me what they think is going to happen after I insert H. What's the process? Yes, in the back. Absolutely right. So initially we'd put in H, it'd be separate, and then we have a property where it's a power of 2. A is before H in the alphabet, so it'll go like this. Does that make sense? If I skip back and I did H and A, H would initially be by itself, then A would be over here, and then A would be deemed to be smaller than H, so A would be there. So A and H, that would produce the same result. All right, the next one is B. So Lydia is correct, H under A. So what are we going to do for B? What's going to happen when I insert B? Yes. Absolutely right. It's going to create a new one, and it's just going to be by itself. So now I'm going to insert G. What do you think is going to happen? If you understand this, you'll be in really good shape for the exam problem. Yes. Absolutely right. 100% correct answer. What's going to happen? So I'm going to press pause so that I can do step by step. When I insert G, what's going to happen is it's going to initially be by itself. Then it's going to make a pair. It's greater than B. So we're going to see that B is going to be here. And then the last step is that B and A, since we have 4 elements and that's a power of 2, it's going to say, well, which one is smaller, A or B? B is larger than A, so A is going to be smaller, so A is going to become the new parent like so. And so now what I want to do is I'm going to insert the next 3, because it's going to be the exact same process. And now I'm going to insert the letter E. So I'm going to press pause, and I'm going to say that this is going to produce the exact same thing. D is greater than C, so C is going to be below D. And what's the last step on this insertion? What's going to happen next? Yes. Absolutely right. So C is going to become below A. So this is the end before we remove the element. So now the problem is going to say remove the smallest element. So I haven't told you exactly how to do this yet, but I want to see if there are any theories. So what's going to happen here is we initially have, it's going to remove the letter A. So what is the property of binomial heaps that all of the other elements in the binomial heap have? Yes. Absolutely right. So we have 2 to the 0, 2 to the 1, and 2 to the 2, right? And so all of these are going to be their own binomial heaps. So what's going to happen is I'm going to remove smallest. And what's going to happen is it's going to remove that element, and then it's going to put them in order by the smallest to the largest value. Like so. So here's the next question. And this is crucial, and I actually got a question in office hours about this. So I have this binomial heap. How would I know which element is the smallest? Yes. Absolutely right. We look through the top element. So we have H, B, and C. And in this case, we know that B is there. So the benefit of a binomial heap, and so what we want to compare this to is a min heap, right? So we studied min heaps earlier this semester, and we have a binomial heap. And so why are binomial heaps considered an improvement over min heaps? The reason why is because when we structure binomial heaps this way, and we take advantage of a mathematical property, we don't have to worry about heapifying all the way down. What's going to happen is it's going to check the subchildren. So I'm going to clear this out and show you the benefit. So I'm going to skip back, and we see that we have A. When A is removed, when A is before A is removed, A is the only element there, right? So all we got to do is create a new array of these elements, and we're going to sort them by the smallest value. So I'm going to remove smallest and step forward. So now, here's what's going to happen when I remove the next smallest. The next smallest is going to find it, and I look through and I do the comparisons, and I find that B is the smallest value. And so when B is removed, that's going to move G up. Did everybody see that? Then what's going to happen is I have a comparison. G is less than H, so therefore it goes there. Let me go through that steps because I see several of you are taking notes. So I'm going to step back, and I'm going to we have B in there. So what's going to happen is it's going to go through and find the smallest value. It identifies B as being the smallest. And then it's going to say, all right, well, it was 2 to the 1. I'm going to take G over here. And then I'm going to put it back into this array. I notice that I have 2 to the 0s. I can add those together and get 2 to the 1. And I know that G is less than H. So therefore, I pair those together, and that becomes my smallest value. Now I'm going to remove smallest again. This time it's going to be C. So we see that remove smallest, it finds C. And now what's going to happen is I have these 2 new values that I want to put in. And it's going to put in F, and it's going to put in D and E. What do you think is going to happen in the next step? So we have one last step before this binomial heap is complete. Does anybody have any ideas? Yes. Absolutely right. It's going to be combined the 2 with the 2 to the 1, and I bet that's what's being. So I'm going to let the student who's typing make their comment, and then it goes under D. So that is absolutely right, Sebastian. When we step forward, we see that G is going to go below D, like so. And so since F is over there, it becomes its own thing. So question in the Slack is stated, could you repeat what the benefit of the binomial heap is? So let me go to the last slide from lecture 25. I'll just open the PDF for simplicity. And I'll go over this comparison of priority queues. So we initially did a sorted doubly linked list. The benefit is that we can access the element at the top in big O one time guaranteed, and it's already going to be sorted. However, the drawback is that in order to sort out all n elements, it requires a worst case big O of n squared time. The next thing we need to consider is implementation 2, that's a min heap. So the min heap is better than the sorted doubly linked list in the average case. It only takes log of n as opposed to n log n as opposed to n squared. And when you start comparing that over time, that gets a significant improvement. Furthermore, we're able to heapify, which means we know that the smallest value is going to be there in worst case log of n time. However, there's no sorting, and it can be a little complicated. So with binomial heaps, we're able to get all this benefit of the log n of insertion, plus it's easier to find the smallest value because it's going to be in that array. So the worst case scenario will be log of n. And we saw the example where we had 8 elements and we only had 3 at the top. So that gives us log of n. And then because of this benefit, we're able to, if we wanted to do a union of priority queues, it would actually be an improvement over minimum heaps. So in not in data structures, in algorithms, this is going to be the first step towards another data structure that's going to have a, actually in the algorithms course, you'll end up spending an entire week on it. It's called a Fibonacci heap, which actually combines the ideas of min heaps and binomial heaps there. But instead of doing it binomially, you'll follow the Fibonacci sequence. And so you'll actually gain even more improvement there. Right. So please let me know if that addressed the question about regarding comparison to the priority queues. All right, so let me go past here. And I forget exactly which one it was. I believe it's C. So if you do C, that will be 30 points towards your assignment, and I'm happy to hear that that addressed the question. So now what I would like you to do is I want you to take a little bit of time, and I want you to do problem 4 on your own, and then we'll work through the solution together on the whiteboard. So please take 3 minutes to work on this. All right, so I have the Slack open on my phone as well, but I want somebody to walk me through and tell me what the binomial heap will look like after the first 4 insertions. So here I have 1, 7, 5, and 2. So what's the process that I'm going to work through in order to get to this solution? Yes. Mm-hmm. Very good. Mm-hmm. Absolutely right. So here's the process. I'll draw it out. First, it'll be 1 by itself. Then we would put in 7. 7 would initially be by itself, but then would be underneath 1, like so. Then I would insert 5, and then 2 would go underneath 5, like so. And then, because we now have this power of 2, and 2 is greater than 1, this step will initially be 1, 2 and 5 will be over here, and then 7 will be there. So very good. So that's the first 4. Now what's the next 4? Who wants to give this a try? Check the Slack. So I see that's have somebody who wants to respond in the Slack. Does anybody else want to give it a shot too? Yes. All right, so far so good. So outstanding. And then there's 2 more steps. And then I think this is what you were saying, that 6 is going to be under 3. And then there's one last step, and I'll let this, the next 4 of the same process, then 3 under the root goes under 1. So Connor, you're absolutely right. This last step here, we now have 1, 2, 5, 7, and then 3 will be over here, 6, 4, and 8. So here we have everything before remove minimum. Does anybody have any questions about that before I continue? All right, so who would like to tell me the final step? I want to remove the minimum. So what's this actually going to look like? Yes. Absolutely right. So the final ordering, we will remove 1, and then these elements would be moved up, and those are the elements that would be searched if we were looking for remove min. So what's going to happen is it'll be ordered 2 to the 0. It'll be in this specific ordering. So here we would have 7. It would be 2 and 5. Then we have 3, 6, 4, and 8. So the benefit here is now I can just say, well, 2 to the 3 is 8. 2 to the 3 minus 1 is equal to 7. So there's 3 elements that I need to look through in order to figure out which one's the minimum. Does that make sense? So now, if I want to remove the minimum again, what's going to happen is it'll say, well, which one's smaller? 2. Which one's smaller, 2 or 3? Now I know that this is the one that I want to remove the element from. So what's going to happen next is this gets deleted. 5 comes up. We see this is 2 to the 0 and 2 to the 0. They get combined together. 5 would be less than 7. So they get put together, and that would be the final binomial heap after 2 removals. So I see there's 2 questions in the Slack. The first question is, could you explain why 6 goes under 3 instead of creating its own binomial pair? So what happens is, when we get to a power of 2, so what happened at this particular step is we had all of this, and then we had 3, 4, 6, and 8, right? And over here we had 1, 2, 5, and 7. So that was the step we were at, and that's why I'm addressing the question in the Slack. So the question is, why does 6 go under 3? So what happens is we already have a 2 to the 2, and we have two 2 to the 1s, right? Does that make sense so far? What we're going to do at that stage is we look at those two and we say, well, which one's smaller? 3 is less than 6. So therefore, when we combine them, what's going to happen is 3 will be the highest one, and then 6 and 8 will be beneath it. So that way it will look like this. It'll be 3, 6, 8, and 4. The reason we do it this way is let's say that this particular heap is the entire heap, and I want to remove min. I know that I can remove 3, then I have a 2 to the 0 and 2 to the 1, so this becomes 4, 6, and 8 is the remaining binomial heap. And if you look at this particular binomial heap, one of the benefits of this binomial heap as opposed to a min heap hopefully would become a little clearer, because now I have 2 elements, and all I have to do is compare those 2 elements. As the binomial heap scales, it will become easier and easier compared to the number of elements n to determine what the smallest value is. And when you remove it, all of the elements are closer. So we had 3, I removed 1 element in that case, and then I now know that log 2 of n, one of those 2 elements, therefore, or 6, will be the smallest value. So please, first, for that student, please let me know if that addressed your question. Second question, so after removing the minimum, we sort the elements heaps by size. Yes, we do that. Next question is, what happens if there's a case with 9 numbers inserted and the minimum is removed? That is an outstanding question. So let me come back up here and go to the animation, since I've run out of room on the whiteboard. And so when we have 9, here's what's going to happen. Share screen. Hide floating mean controls. Lecture, and so I'm going to press refresh, and I'm just going to do 1, 2, I'm going to insert 9 elements. And so when you're studying for an exam, so while I'm doing this, mess around and see if you can figure out some weird situations. So if I put in 9, I know that, oh, 9 goes below 5. Now if I put in a value in the middle, that's good. And if I put in 7, this will make 7 above 8, and then 7 will be below 5. And now we have an 8th element. And let me put in 10. So now what's going to happen is I have the smallest element is either 1 or 10, right? So here's what's going to happen next. It's going to remove 1 and then put everything in order. So I remove the smallest. It compares 10 and 1. 1's the smallest value. Then it's going to break up all of these elements. And then we put in that first element here. So this is going to address the next question is there a reason the new values are placed on the left before they become 2 to the 2? Here is why. Do you see that we currently have 2 values that are 2 to the 0? Does everybody see that? So now what we're going to do is like, well, we can combine these. 2 will go above 10. You put everything here, so 2 will go above 10. 2 is less than 3, so therefore 3 is going to get combined here. And now we have 2 to the 2's. So now we can combine these together. 2 is less than 5, so therefore 5 will become a subchild of 2. Does that make sense to everybody? Please let me know. So there's 2 students. Please let me know if that I kind of had a combination of addressing your questions. I think it's D. Yes. So at this point, if you do ls, you should have prob1.text through prob4.text completed. All right, does anybody have any other questions about binomial heaps before I go on to cuckoo hashes? All right, so the main idea behind what we're eventually going to call a cuckoo hash is an idea that was initially called Robin Hood hashing. And the idea behind Robin Hood hashing is that I am able to, instead of probing to the next element, what I'm going to do is I'm going to say, well, I'm going to hash 7, and I'm going to say I want to hash so mod 8. So it's going to be 7 mod 8 is going to be 7. 15 mod 8 will be 7. So I try to hash 15 there, right? And what we learned about in linear probing and quadratic probing was that we would say, well, a 7 is already in that hash. I need to take 15 and move on. The idea behind a Robin Hood hash is that it's going to say, well, 15 was the most recently hashed value. So I'm going to put 15 in that bucket, and I'm going to take the older bucket, the older value in the bucket, in this case was 7, and I'm going to use that as my next hash. Does that make sense? So double hash meant I would use the second hash to go to the second value for the most recently used hash value. Whereas with Robin Hood hashing, I want the most recently hashed value to go in the bucket and then take the least recently used value and put that in the second hash. The least recently used is a concept you will encounter again in the algorithms course and in the operating systems course. Using these queues and these kind of hash tables to maintain caches, that is another, we already saw that just recently with splay trees. There's all kinds of different data structures and approaches that you can use to determine whether or not, how you want the computer to operate. So queues, you'll see them a lot when you're trying to schedule tasks in an operating system. Specifically, which level, where in the queue should it be the most recently used or the least recently used? And you can make that kind of decision because we understand that queues underneath are doubly linked lists. And doubly linked lists have a head and tail pointer. And so we can access either the one at the beginning or the one at the end. So depending on your operating system's approach, you can use either one of those. And you know you can do that because of your understanding of how the data structure is structured. So that is why here at the bottom in the benefits, I say cache-friendly and memory efficient. Just like a splay tree, in a splay tree, all the values that we most recently accessed are near the top. This allows us to be able to keep track of the cluster of elements. So we're seeing this temporal and spatial locality. With this particular, what's eventually going to use as a cuckoo hash, the elements that are hashed there, most recently hashed, will only require one hash function to be able to look up the result, or are more likely to only need one instead of having to go through. So this is good in what you'll eventually learn about, something called a transition look-aside buffer. In an operating system, that allows you to be able to do virtual memory. So those of you who've coded in Java, these kind of data structures enable the use of a programming language like Java. So this is something that while you're working on it now, bear in mind that these are things that you're going to see over and over again in computer architecture, in operating systems and algorithms, and this will set you up for success in the future. So what I'm going to do is I'm going to go over an example of a Robin Hood hash problem. There will not be a Robin Hood hash problem on the exam because anything I can evaluate with a Robin Hood hash, I will also be able to evaluate with a cuckoo hash. The reason I'm going through the problem, though, is because I want you to get the idea of how the Robin Hood hashing works. So what I have here is a regular Robin Hood hash. And the idea is I'm going to insert values, and I have two hash functions, just like a normal double hash. So normally what would happen with a double hash is that I would, once I have a collision, the newer value would be using the second hash function. But in that case, it's going to be flipped. So what's going to happen is I have a hash function k mod 7. So 21 mod 7. I apologize. Those should say k mod 11. 21 mod 11 is going to be 10. And then I'm going to do 7 mod 11 is going to be 7. And then 18 mod 11 will be 7. Before, I would put 18 into the second hash. So that's what we did with double hashing. With a Robin Hood hash, I am going to put 18 in bucket 7, and then I'm going to put the value 7 into the second hash. So here's the first step. 18 mod 11 becomes 7. So 18 is now in the bucket. That's the most recently used. Now 7 is available. And so now I'm going to put 7 into the second hash function. So 7, I'm just going to bring up Epic Pen. So the whole idea, for those of you who maybe need a refresher, that bottom k divided by 7, that basically says, give me the value without the remainder. And so in this case, 7 divided by 7 will be 1. So 1 mod 11, excuse me. I'm sorry. 7 mod 7 will be 0. (44) mod 7 will be 2. And then 93 mod 7, we put 44. That's the most recently used. And then 93, we put that into the second function there. Okay, so just like a double hash, there is this potential for a cycle, right? And so what we did in linear probing and quadratic probing and double hashing is that when the hash function got halfway filled, we just rehashed everything, right? And so that added some overhead, and we had this worst case amortized insert of big O of n for a hash table, but most of the time it's big O of 1, and access and find were big O of 1 over time as well. The question is, since this is more of an advanced hash table and we're trying to figure out how to beat the conventional standard template libraries, is how can we use this knowledge to be able to do that? And this solution to this is going to be known as cuckoo hashing. And cuckoo hashing is going to have at least 2 hash functions and will have 3 different arrays. So instead of 1, it's going to have 3. And so the first idea is that, okay, so I've just said that already. So if we're going to do these locations, this will allow us to be able to move all the elements. So what's going to happen is I'll have 3 different hash tables. Each one has its own hash function. So I will keep moving the element using this Robin Hood hashing to be able to determine where the next value should go. And so I'm going to work through an example, and then this will be the next one. And yes, it should have been 1, not 0. All right, so I've included a link here. If you want to go into the deep mathematical proof on this, you're more than welcome to. But the general idea with the cuckoo hash is because of the Robin Hood hashing, and because of the fact that we're using 3 underlying arrays instead of 1, what we will be able to do is we will be able to significantly improve the number of buckets that can be filled before we would encounter a cycle. So 91% of the time with the cuckoo hash, we will be able to, we'll be able to fill up 91% of the values of the buckets before we need to rehash. So that's the benefit of this particular data structure that we are using. Okay, so given the following 3 hash functions, show the insertion for the following elements. So for the first bucket, we're going to do k mod 7, and here we have 7 values in the bucket. Likewise, k divided by 7 mod 7, and then for 2, this should be k plus k divided by 7, and all of that is going to be mod 7. So let's go through the result here. 42 mod 7 is 0, and so that's free. 93 mod 7 is 2. 79 mod 7 is 2. So what's going to happen is 72 will be put in this bucket, and we're going to push 93 out. And so what's going to happen next is 93 is going to go down here. So 93 divided by 7 is 13. Mod 7 will give us 6. Does that make sense so far? So now we go back to 79. 79 will go to the first hash function. So 79 mod 7, I'm sorry, not 70, it should have been 70. Okay, just, this should say 79. All right, so 11 mod 7 is 4, so that bucket is empty. We're going to use that. And then 22 mod 7 is going to be 1. That's free. Then we're going to do 34. 34 mod 7 is 6, so that's free. Then we're going to have 9 mod 7, that's going to be 2. So now we're going to take 72 out. 72 was here, and now 72 is going to move over. And then 72 divided by 7 is going to be 10. 10 mod 7 is going to be 3. The next value we're going to insert 44. 44 mod 7 is 2. So now 22 is here. And then we push 9 out. So 9 divided by 7 is going to be 1. 1 mod 7 will be 1. So 9 will end up in bucket 1. Does that make sense? All right, I see there's a question being typed. Well, I'll just keep going. So now the last thing, 15 mod 7 is going to be 1. And so 22 was here, now 15's here. 22 divided by 7 is going to be 3. 3 mod 7 will be 3, and we see that 72 is there. So what's going to happen is 22 is going to be pushed here, and 72 will be moved. Does that make sense? And then the last step is 72 is going to be put into this function here. So 72 plus 72 divided by 7. In this case, this is going to be 72 plus 10. So you're going to get 92 mod 7. And we see that's what's going on here. 72 mod 7 comes out to 1. I'm sorry, 92 mod 7 comes out to 1, and we see that 72 is hashed there. So I will describe the benefit of the Cuckoo hash by going over this solution, then I'll address the question in the Slack. So the benefit, we see here that we have the first bucket, and that the values 42 and 15, this should be 44, 11 and 34, these were buckets that were most recently hashed, right? So that means that we can use these in lookup tables because those are elements that have been accessed most recently. To follow up with the question on the Slack about if we have 3 hash functions, we want a hash function for each bucket, set of buckets. So on the exam, there will be 3 buckets. There'll be 3 hash tables and 3 hash functions. All right, so same thing. We have 15 mod 7 is 1. 19 mod 7 is 5. 34 mod 7 will give us 6. 7 mod 7 will give us 0. 16 mod 7 will give us 2. 17 mod 7 will give us 3. 21 mod 7 will give us 0. So 21 gets put in bucket 0, and we push 0. So now 0 divided by 7 is 0. 0 mod 7 will be 0, so it goes there. We're now going to put in 26. 26 mod 7 is going to be 5, so that's the first hash function. So now we're going to remove 19, which was here. So 19 divided by 7 will give us 2. 2 mod 7 will be 2. And so now we're going to put in 9. 9 mod 7 is 2. That will bump out 16. 16 divided by 7 is 2. So now 16 will go in bucket 2, and 19 will be pushed out. So then 19 plus 19 divided by 2, which is 2, that's going to be 21 mod 7, which is 0, which will be there. And so question in, if 72 caused a, what would happen? If 72 caused a collision, then we would go back and put it into, we would be investigating the initial hash with the next value. So what do you mean, like, which in the last? So Connor, I need help understanding what you mean. So with 72, are you talking about this particular problem or the last problem? The last one. Okay, so I need to scroll all the way back to address your questions. I'm going to finish this problem and then get back to your question. So if we do 31 mod 7, 31 is put into the bucket. And then it pushes 17 out. And then 17 divided by 7 is 2. 2 mod 7 is 2, so now it's going to push out 16. 16 plus 2 is 18. 18 mod 7 is going to be 4. And then we're putting in 4. So 4 goes in there. Then we put in 23. 23 mod 7 is 2. Now we're pushing 9 out. 9 divided by 7 is 1. So there's no value in bucket 1. We see that's put there. And then last thing we're going to do is 11. 11 mod 7 is 4. So now we're going to move 4 out. 4 was in that bucket. 4 divided by 7 is 0. So we'll push 0 out. 0 now. 0 plus 0 mod 7 is 0. And I think this is actually going to be a roundabout way of addressing the other question that's in the Slack. So let's say I move this and I want to put it back to 19. So now this is where we're going to make sure that we don't have a cycle. 19, we have a full bucket in the first column. 19 mod 7 is going to be 5. So 26 is going to get moved. So we push 26. 26 divided by 7 is going to be 3. So that's going to be 3 mod 7, which is 3. So that is how we avoid the cycle there. Okay. All right, does any, so the thing is that it will continue to do that. So that's what would happen with 72 if you tried to rehash it, what would happen there. So the way a problem would come out on the exam would be that there will be 3 hash tables, a set of values, and there will be 3 hash functions. So what I would like you to do, let me go through everything, is I want you to run make problem 5, and the way this problem is going to work, and this is the one you should have downloaded, is it gives you a set of cuckoo hashes and a set of insertions and a set of functions here. So given 3 hash functions, so these are actually the same 3, show the insertions for the following elements in a cuckoo hash. So we have 24, 16, 17, 23, 65, and 9. I avoided the cycle because the value that was being bumped out had not gone through the cycle yet. So that's why 26 was going through, not 19. So a question in the Slack, could you think of this as a normal double hash if you insert from right to left? And I would discourage that because it would just be the same thing. You would want to start moving other elements. The double hash does not grab a value from the previous hash, so it's not quite the right analogy. But you can think of it as a Robin Hood hash in the opposite direction. Yeah, please let me know if that addressed your question. Okay, who would like to tell me the first step? What's the first thing we're going to do here? Yes. Hash 24 to 3, very good. So 24 mod 7 is going to be 3, so 24 will be here, very good. So now we're inserting 16. So what do we do now? Yeah, go ahead. 16 to bucket 2, outstanding. So now we're going to insert 17. So what is, and so I'm going to bring up the Slack here on my phone as well, so that way I can hear contributions for the whole class. I see that someone is typing, so I'm going to let that student type. So what is the steps that we're going to do here in this specific problem? Yes. Very good. All right, so I'm going to, so Selena says 17 to bucket 3 and rehash 24, which is exactly what was said here. So simplest way to do this on exam, give yourself enough space on the sheet and then put 17 here. So now we go to 24. 24 divided by 7 is going to be 3. And then 3 mod 7 is 3. So 24 will go here. I'm sorry, did I say 17? My apologies. 17's here, 24 goes there. Yeah, there, no, we were right. Okay, so next one is 23. So what are we going to do now? Yes. 23 is going to be 2, right? So as you correctly said, we're going to put 23 here, and now we're going to go to 16. 16 divided by 7 is going to be 2. 2 mod 7 is 2, so 16 will go here. Does that make sense to everybody? 23 to bucket 2 and rehash 16. Outstanding. Both Lydia and Selena. So now we're going to do 23. Now let's do 65. So 65, what are we going to do? What's my first step? I see there's lots of typing going on in the Slack too. Who wants to take a guess at this? Yes, go ahead. Very good. So 65 will go here. So now we're going to move 23 up. So where's 23 going to go? (23) to bucket 2 and replace 16. 23 divided by 7 is going to be 3. 3 mod 7 is 3. So now we're going to take out 24. And now we're going to put 24 up here. And 24 divided by 7 is 3. 24 plus 3 is going to be 27. 27 mod 7 is going to be 6. Yeah. 27 mod 7. Yeah, 28 mod 7, 27. So 27 is that result. So the way this worked was 24 plus 24 divided by 7, which is going to be 24 plus 3, which is equal to 27. 27 mod 7 would be 6. And the mistake that's often made is putting 27 here instead of 24. Okay, so the question, and I'll get to the questions about the calculator in a moment. So hold on for that. Okay, so last one, 9, right? 9 mod 7 is 2. So now we're going to go with 65. 65 divided by 7 is 9. 9 times 7 is 63. So that's going to be 9 mod 7 is 2. 65 is here. And now it means we're going to move 16 up. 16 divided by 7 is 2. 16 plus 2 is 18. 18 mod 7 is 4. Then we make sure that we put in 16 here, like so. So the final solution should be 9 and 17 in bucket 3, 5 and 23 in buckets 2 and 3 in the second one. And the third one should be 4 and 6, containing 16 and 24 respectively, which I believe is choice C. Okay. Does anybody have any questions on this? Once you put in this value, we see that that's exactly, it was choice C. We'll clear that out, like so. All right, to review, for the cuckoo hashing, as there are more locations and better distribution, requires fewer hashes. we're able to take advantage of this to exploit hashing, specifically with caches. Okay. And we can take up more, almost 90% of the buckets without having to rehash. Hey, does anybody have any other questions? How do you know when to stop re-looping through the hashes and move to a rehash? So if we go through twice, then you need to rehash. You will not encounter a situation like that on the test. Does anybody have any other questions? Yes. Do you have a question, or you just? Should the size of the table still be a prime number? Yes, they should all be there for the exact same reason as before, to ensure a more even distribution in the event of uneven keys, especially if we're trying to use this for a cache efficient data structure. That's when we might want to do something like that. Any other questions about cuckoo hashing? All right, so the exam expectation. There will be a cuckoo hash problem on the final. I will not ask a Robin Hood hash question, because anything that I could evaluate on a Robin Hood hash would be this exact same thing, and that would be redundant. All right, so guess what? You did it. That's officially the end of the material for this course. So you survived. So here's what's going to happen next week. Next week, there's no lab on Monday and Tuesday. Use that as a code sprint opportunity to complete your pre-internship projects. On Tuesday, I will have an in-depth exam review, at which point I will go over in detail what we're going to be doing on the exam, including 2 questions that I got on the Slack. You will be permitted the use of a non-memory calculator. So if you bring in like I think it's a TI-82 or TI-84, and it has memory, you need to show me that you've cleaned it out, or show one of the TAs, right? So that way you can do the logarithm problems, particularly for calculating out the size that you would require for a Bloom filter. So you could do things like this. We will go over the detailed expectations for the final exam. I will be bringing in, I have already ordered individually wrapped popcorn snacks, so you have an opportunity to relax as well. And you will have a in-depth lecture from the pup professor, who will be lecturing on the best way to store pup snacks and to be able to how to fetch things as fast and efficiently as possible. Just to give you a, bring this over here. So the final exam study guide and all the videos are already there and available for you. If you go to the main lecture page and go to lecture 27, this is the stuff we'll go over. I have a course review already there. I have the final exam review guide is already there. In addition, I'll kind of briefly go over the future course information and future interview study guide links that I have there as well. All right, does anybody have any questions on cuckoo hashing that we covered today? And we'll go into a lot more detail on Tuesday when I do the final exam review. On that note, if no one has any other questions, then you are free to go. Neat.